When you step outside on a night away from the glare of cities and look upward, the sky appears crowded with light. Stars puncture the darkness everywhere you turn. The Milky Way sweeps across the heavens like some celestial river. It creates this impression of abundance, this feeling that space must be packed with matter and energy. But this impression deceives you completely. Every star visible to your unaided eye exists within your immediate cosmic backyard. The most distant ones you can perceive without optical aid sit roughly 15,000 light-years distant. That seems impossibly far by human standards, yet our galaxy stretches 100,000 light-years from edge to edge. You're glimpsing less than 15% of just your own galaxy. And your galaxy represents merely one among hundreds of billions scattered throughout observable space. That sky seemingly bursting with stars. It's just your neighborhood. It resembles standing in your yard and assuming the entire planet must look identical to that small patch of ground. Now introduce a telescope into this equation and observe what emerges. Aim a powerful telescope toward what appears as absolutely empty darkness between stars. Select a region containing nothing whatsoever visible to unaided vision, pure blackness. The Hubble Space Telescope performed exactly this experiment back in 1995. They directed the instrument toward a minuscule patch of sky within the constellation Ursa Major. This patch measured so small that you'd need 12 million identical patches to cover the entire celestial sphere. Within that tiny dark region, Hubble stared continuously for 10 days. Long exposure after long exposure, collecting every photon arriving from that direction. What emerged from this observation? Approximately 3,000 galaxies. Entire galaxies compressed into a region of sky, matching the size of a sand grain held at arm's length. Every blob of light in that image represents a galaxy harboring hundreds of billions of stars. This became known as the Hubble Deep Field, and it revealed something profound to astronomers. Everywhere you direct your gaze, even into the darkest patches of sky imaginable, galaxies exist. Billions upon billions of them. They repeated this experiment targeting other patches of sky. Identical results emerged. Galaxies everywhere. Distant galaxies, nearby galaxies, spirals, ellipticals, irregular galaxies colliding and merging. So the universe must overflow with matter, correct? All these galaxies packed everywhere you look surely means the universe is dense with material. But here's where mathematics reveals a different story entirely. Let's calculate the actual amount of matter existing out there. The observable universe measures approximately 93 billion light-years in diameter. That's the farthest we can observe in any direction. Light has traveled for 13.8 billion years since the Big Bang. But the universe has been expanding throughout that entire time. So the sources of the oldest light now sit much farther away than 13.8 billion light-years. The observable universe contains approximately 2 trillion galaxies. That's 2,000 billion galaxies. Each galaxy harbors somewhere between 10 million and 1 trillion stars depending on the galaxy's size. The average probably sits around 100 billion stars per galaxy. So 2 trillion galaxies times 100 billion stars per galaxy gives us roughly 200 billion trillion stars. That's 2 followed by 23 zeros. 200,000 billion stars. That sounds substantial. It is substantial. But now calculate how much space those stars actually occupy. A typical star like our Sun has a diameter of about 864,000 miles. The volume of a sphere equals 4/3 times pi times the radius cubed. Plug in the Sun's radius and you get approximately 1.4 billion cubic miles. Now multiply by 200 billion trillion stars, and you get the total volume occupied by all stars in the observable universe. Approximately 2.8 times 10 to the 32nd power cubic miles. That sounds enormous. 2.8 followed by 32 zeros. Surely that fills a significant fraction of space. But the observable universe has a radius of about 46.5 billion light-years. Convert that to miles and you get about 4.4 times 10 to the 26th power miles. The volume of a sphere with that radius is approximately 3.6 times 10 to the 80th power cubic miles. Compare those numbers. Stars occupy about 2.8 times 10 to the 32nd power cubic miles. The universe has a volume of about 3.6 times 10 to the 80th power cubic miles. Divide the first by the second, and you get the fraction of space occupied by stars. The fraction comes to approximately 7.8 times 10 to the negative 49th power. That translates to a decimal point followed by 48 zeros, and then 78. Stars occupy less than 1/4,000,000th of 1/4,000,000th of 1/4,000,000th of a percent of space. Let me offer some perspective on this. If you shrank the observable universe down to Earth's size, all the stars combined would occupy a volume smaller than a single atom. Actually, considerably smaller than a single atom, more like a single proton. And that calculation only accounts for stars. Most of a star's volume is empty space too. The nucleus of an atom occupies about 1/1,000,000th the volume of the atom itself. The rest is emptiness where electrons orbit, so even the matter composing stars is mostly void. And we haven't even discussed the space between stars within galaxies, or the space separating galaxies yet. The Milky Way galaxy contains approximately 200 billion stars. The galaxy stretches about 100,000 light-years across. That's roughly 588 trillion miles. The nearest star to our Sun, Proxima Centauri, sits about 4.2 light-years away. That's roughly 25 trillion miles. So the distance between stars is thousands of times larger than the stars themselves. If you scaled the Sun down to a grain of sand 1 millimeter across, the nearest star would sit about 19 miles away. 30 kilometers of empty space separating 2 grains of sand. That's the typical spacing within our galaxy. And galaxies themselves are separated by even more dramatic distances. The Andromeda Galaxy, our nearest large neighbor, sits about 2.5 million light-years away. The Milky Way is 100,000 light-years across, so the distance to Andromeda is 25 times the width of the Milky Way. That's like 2 grains of sand separated by a football field maintaining our previous scale. And between the Milky Way and Andromeda, there are only a handful of smaller dwarf galaxies, mostly just empty space, nothing, vacuum, darkness. And this is within our local group, one of the denser regions of the universe. In other regions, galaxies sit much farther apart. Clusters of galaxies are separated by even larger voids containing almost nothing. So the universe is mostly empty space between stars, with more empty space between galaxies, with even more empty space between galaxy clusters. But we're not finished yet, because there's a deeper problem. Even counting all the stars and all the galaxies, and all the gas and dust between them, we're still missing most of the universe. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma galaxy cluster. This is a large group of galaxies, about 320 million light-years away. Zwicky measured how fast the galaxies in the cluster were moving. He knew the cluster was held together by gravity, with all the galaxies orbiting a common center of mass. From the galaxy's speeds, he could calculate how much total mass must be present to generate enough gravity to hold them together. Then he looked at the galaxies themselves. He counted them, measured their brightness, estimated their mass based on how much light they emitted. And he discovered a problem. The galaxies weren't massive enough. Not even close. Based on visible matter, the cluster should fly apart. The galaxies were moving too fast to be held together by the gravity of visible matter alone. Zwicky calculated that the cluster needed about 400 times more mass than he could see. He proposed that most of the mass must be dark, invisible matter that doesn't emit light. He called it dark matter. Nobody believed him. Dark matter sounded absurd. Invisible matter that somehow had mass but didn't interact with light violated common sense. Scientists looked for other explanations. Maybe Zwicky made a mistake in his measurements. Maybe the galaxies weren't actually gravitationally bound. Maybe our understanding of gravity was wrong on large scales. But as more observations came in over the following decades, the problem persisted. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. She measured how fast stars orbit the galactic center at different distances. In our solar system, planets closer to the Sun orbit faster than planets farther out. Mercury orbits faster than Earth. Earth faster than Mars. Mars faster than Jupiter. This makes sense because gravity weakens with distance. The farther you are from the Sun, the weaker its gravitational pull, the slower your orbit. Galaxies should work the same way. Stars near the galactic center should orbit faster than stars in the outer regions. But that's not what Rubin observed. She found that stars in the outer regions of galaxies orbit just as fast as stars closer to the center, sometimes even faster. This made no sense unless there was additional mass in the outer regions providing extra gravitational pull. Mass that wasn't visible. Rubin's observations confirmed Zwicky's finding. Galaxies contain far more mass than we can see. The visible stars and gas make up only about 15% of a galaxy's total mass. The other 85% is dark matter, and it's not just galaxies. Dark matter shows up everywhere astronomers look. In galaxy clusters in the cosmic web, in the rotation of galaxy groups, in gravitational lensing measurements, in the cosmic microwave background radiation patterns. Every independent measurement points to the same conclusion. Most of the matter in the universe is invisible. We can't see it. We can't touch it. It doesn't emit light or absorb light or interact with electromagnetic radiation in any way. But it has mass. It curves spacetime. It exerts gravitational pull, and it outweighs normal matter by a factor of about 6 to 1. For every kilogram of normal matter, protons and neutrons and electrons, the stuff that makes up atoms and molecules and stars and planets and people, there are approximately 6 kilograms of dark matter. So when we calculated earlier that stars occupy a tiny fraction of space, we were only counting normal matter. Dark matter takes up even more volume, though we can't see it directly. Current estimates suggest dark matter makes up about 27% of the universe's total mass, energy content. Normal matter, everything we can see and touch, makes up about 5%. That means 95% of the universe's mass energy is in forms we don't fully understand. Let's talk about what dark matter actually does, because this is crucial to understanding why galaxies exist at all. Without dark matter, galaxies as we know them couldn't form. The gravity from normal matter alone isn't strong enough to pull gas together into the dense clumps needed for star formation. Here's how it works. In the early universe, hydrogen and helium gas was spread fairly uniformly throughout space. To form galaxies, this gas needed to collapse under gravity into dense clouds. But normal matter interacts with radiation. As gas clouds collapse and heat up, they emit radiation. This radiation carries energy away, but it also creates pressure that resists further collapse. The gas wants to collapse under gravity, but radiation pressure pushes outward, preventing collapse. This creates a balance that's very difficult to overcome with normal matter alone. Dark matter solves this problem. Dark matter doesn't interact with radiation. It doesn't emit light, doesn't absorb light, doesn't feel radiation pressure. So dark matter can collapse freely under gravity without any resistance from radiation. In the early universe, dark matter formed the scaffolding, the framework of structure. Dark matter clumped together first, forming hollows, spherical clouds of dark matter held together by their own gravity. These dark matter halos created gravitational wells, deep pits in the fabric of spacetime. Normal matter, hydrogen and helium gas, fell into these gravitational wells. Once the gas was concentrated by falling into the dark matter halo, it could collapse further and begin forming stars. So every galaxy has a dark matter halo surrounding it. The visible galaxy, the stars and gas we can see, sits at the center of a much larger dark matter halo. The Milky Way's visible disk is about 100,000 light-years across, but its dark matter halo extends at least 600,000 light-years, possibly farther. That's 6 times larger than the visible galaxy, and the dark matter halo contains about 10 times as much mass as all the stars and gas in the visible galaxy combined. So when you look at an image of the Milky Way, you're seeing less than 10% of the galaxy's total mass. The rest is invisible dark matter surrounding the visible parts. Every galaxy we observe has this structure, a visible component made of stars and gas, and a much larger invisible component made of dark matter. The dark matter dominates the galaxy's gravity, determining how fast stars orbit and how the galaxy interacts with neighbors. Astronomers can map dark matter halos by measuring how galaxies rotate. In the outer regions of galaxies, far from the visible edge, there are still gas clouds and a few stars. By measuring how fast these objects orbit, astronomers can determine how much total mass is present, and consistently they find far more mass than can be accounted for by visible matter. This extra mass has a characteristic distribution. It's densest at the center and gradually becomes less dense moving outward. The density drops off much more slowly than the density of visible matter. Visible matter is concentrated in the galactic disk. Dark matter is spread throughout a spherical halo. This difference in distribution is part of what convinced astronomers that dark matter must be something fundamentally different from normal matter. It's not just dark clouds of normal matter, not planets or failed stars or dust. It's something else entirely. Scientists have built sensitive detectors deep underground, trying to catch dark matter particles. The detectors are underground to shield them from cosmic rays and other interference. They're looking for extremely rare events, where a dark matter particle passes through the detector and collides with a normal atom. Such collisions should be incredibly rare because dark matter barely interacts with normal matter. But if you have a large enough detector and wait long enough, you might detect a few events. So far, these experiments have found nothing conclusive. There have been hints, possible signals that might be dark matter, but nothing confirmed. Other experiments are searching for dark matter at particle colliders like the Large Hadron Collider. The idea is to create dark matter particles by smashing normal particles together at extremely high energies. If dark matter particles are created in these collisions, they would fly out of the detector without leaving a trace, because they don't interact with normal matter. But their existence would be inferred from missing energy and missing momentum. The collision's total energy and momentum must be conserved. If some energy and momentum disappears, It must have been carried away by something invisible. That something could be dark matter. Again, no confirmed detection yet. We have several theories about what dark matter might be. The leading candidate is called weakly interacting massive particles, or YMPs. These would be subatomic particles heavier than protons, but interacting only through gravity and the weak nuclear force. The weak nuclear force is responsible for certain types of radioactive decay. It's extremely weak, hence the name, operating only over distances smaller than an atomic nucleus. If dark matter particles interact through the weak force, they would be almost impossible to detect directly but would still have mass and create gravitational effects. YMPs would have been created in the early universe when temperatures were high enough for their formation. As the universe cooled, YMP creation stopped, leaving a certain amount frozen into existence. Calculations suggest that if YMPs exist with certain properties, they would naturally make up about 27% of the universe's mass energy, exactly matching observations. This remarkable coincidence is called the YMP miracle, and it's why YMPs are considered the leading dark matter candidate. But YMPs haven't been detected despite decades of searching. This has led some physicists to consider alternatives. Axions are another candidate. These are hypothetical particles much lighter than YMPs, possibly 1,000,000 times lighter than electrons. Axions were originally proposed to solve a different problem in particle physics, but they could also account for dark matter. If they exist, there would need to be enormous numbers of them to make up the required mass. But because they're so light, they would behave differently from YMPs, forming structures on different scales. There's also primordial black holes. These are black holes that formed in the early universe from density fluctuations, not from collapsing stars. If enough primordial black holes formed with the right mass range, they could account for dark matter. They would have mass. They would create gravitational effects, and they wouldn't emit light. But there are observational constraints that make this unlikely. We don't see the gravitational lensing effects that large numbers of black holes would produce. Some physicists have even proposed that there is no dark matter, and instead our understanding of gravity is wrong on large scales. This approach is called modified Newtonian dynamics, or MOND. The idea is that gravity doesn't follow Newton's inverse square law exactly when gravitational fields are very weak. In galaxy-scale gravitational fields, gravity might be stronger than Newton predicts, eliminating the need for dark matter. MOND can explain galaxy rotation curves fairly well, but it struggles to explain other observations like galaxy clusters and gravitational lensing, and the cosmic microwave background patterns. Most physicists favor dark matter over modified gravity because dark matter explains more observations more consistently. But until we detect dark matter directly, modified gravity remains a possibility. The point is we know dark matter exists because we can measure its gravitational effects, but we don't know what it is. It could be YMPs or axions or primordial black holes or something we haven't thought of yet. This is one of the biggest unsolved mysteries in physics. We're trying to understand what constitutes 27% of the universe's mass, and we have no confirmed answer. And this mystery makes the universe feel even emptier. Not only is space mostly vacant, but most of the matter that does exist is invisible and unknown. We're surrounded by dark matter right now. It's passing through you constantly. Billions of dark matter particles flowing through Earth, through buildings, through your body every second. You don't feel it because it doesn't interact electromagnetically. It doesn't collide with the atoms in your body in any meaningful way. It just passes through like you're not even there. The only reason we know it exists at all is because we can measure its gravitational effects on galaxies and galaxy clusters, and the universe's large-scale structure. But on human scales on Earth, in our solar system, dark matter is completely imperceptible. It's there, it has mass. But it might as well not exist for all the effect it has on daily life. This is what makes dark matter so strange. It's the majority of matter in the universe. It outweighs normal matter 6 to 1. It's essential for galaxy formation. Without it, galaxies wouldn't exist, stars wouldn't form, planets wouldn't form, life couldn't arise. And yet we can't see it, can't touch it, can't detect it directly, and don't know what it is. It's like discovering that most of your house is made of invisible materials you can't see or feel but must exist because the house is standing. And it gets worse because there's dark energy. In 1998, 2 independent teams of astronomers were studying distant supernovas. These are exploding stars that briefly shine as bright as entire galaxies. A particular type of supernova called Type I has very consistent brightness. Let me explain why Type I supernovas are so useful. A Type I supernova occurs in a binary star system. 2 stars orbit each other gravitationally. One star is a white dwarf, the dense remnant of a dead star, roughly the mass of the Sun compressed into the size of Earth. The other star is a normal star still burning hydrogen. The white dwarf pulls matter from its companion star. This matter accumulates on the white dwarf surface, adding to its mass. When the white dwarf reaches a critical mass, about 1.4 times the mass of the Sun, something catastrophic happens. This critical mass is called the Chandrasekhar limit, named after Subramanian Chandrasekhar, who calculated it in 1930. At this mass, the pressure at the core becomes so intense that carbon fusion suddenly ignites. Carbon fuses into heavier elements in a runaway nuclear reaction. The entire star explodes in seconds, releasing as much energy as the Sun will emit over its entire 10 billion year lifetime. The key point is that this always happens at the same mass, 1.4 solar masses. Every Type I supernova reaches this mass before exploding. And because they all explode at the same mass, they all release roughly the same amount of energy. They all reach roughly the same peak brightness. This makes them standard candles, objects whose intrinsic brightness is known. If you observe a Type I supernova and measure how bright it appears from Earth, you can calculate how far away it is. Simple inverse square law. If an object is twice as far away, it appears 4 times dimmer. 3 times farther away, 9 times dimmer. Measure the apparent brightness, know the actual brightness, calculate the distance. This is one of the most reliable ways to measure distances to very distant galaxies. In the 1990s, 2 teams decided to use Type I supernovas to measure the universe's expansion rate. The High Z Supernova Search Team and the Supernova Cosmology Project. Independent groups using independent methods, cross-checking each other's results. Their goal was to determine whether the universe's expansion was slowing down, and if so, how fast. They would find distant supernovas billions of light years away, measure their distances, and measure their redshifts. Redshift tells you how fast a galaxy is receding. Light from receding objects is stretched to longer wavelengths, shifted toward the red end of the spectrum. The more red-shifted the light, the faster the recession. By comparing distance to redshift for many supernovas at different distances, they could construct a relationship between distance and expansion rate over cosmic history. This would tell them how fast the universe was expanding at different times in the past. Everyone expected the expansion to be slowing down. After the Big Bang, the universe started expanding rapidly, all matter flying apart. But matter has mass. Mass creates gravity. And gravity pulls things together. So over time, gravity should slow the expansion. The question wasn't whether the expansion was slowing, but how much. Was there enough matter to eventually halt the expansion and cause the universe to recollapse? Or would expansion continue forever, but at an ever-decreasing rate? Finding the answer required very precise measurements of very faint, very distant supernovas. Both teams spent years searching for supernovas, observing them with the largest telescopes available, carefully analyzing the data, and in 1998, both teams announced their results independently. The distant supernovas were fainter than expected, not by a lot, but by a statistically significant amount. Fainter means farther away, and farther away than expected means the universe expanded more than predicted. The only way this makes sense is if the expansion rate increased over time instead of decreasing. The universe's expansion is accelerating. This was completely unexpected, shocking to the physics community. Many physicists initially thought it was a mistake, some systematic error in the observations or analysis, but both teams found the same result independently. And as more supernovas were observed over the following years, the signal became stronger and clearer. The acceleration is real. Something is pushing space apart, counteracting gravity. We call it dark energy, but that's just a label for our ignorance. We have no idea what it is. The simplest explanation is that dark energy is a property of space itself. Empty space has energy. This sounds strange, but it's predicted by quantum mechanics. In quantum field theory, even empty space isn't truly empty. It's filled with quantum fields that permeate all of space. These fields have a ground state, a lowest possible energy level, but this ground state has a non-zero energy density. Even in empty space, the quantum fields contribute a certain amount of energy per cubic meter. This is called vacuum energy or the cosmological constant. Einstein actually proposed a cosmological constant in 1917, not because he knew about quantum fields, but because he wanted to make the universe static. At the time, everyone believed the universe was eternal and unchanging. But Einstein's equations of general relativity predicted that the universe must be either expanding or contracting. It couldn't be static because gravity would pull everything together. Einstein added a cosmological constant to his equations, a term representing a repulsive force that could balance gravity and keep the universe static. He called it his biggest blunder after Edwin Hubble discovered the universe actually is expanding. But now, 80 years later, observations suggest the cosmological constant might be real after all, though for different reasons. If space has a non-zero vacuum energy density, and that density remains constant as space expands, then as the universe grows larger, the total amount of vacuum energy increases. More space means more vacuum energy, and this energy has a repulsive effect, causing space to expand faster. This creates a feedback loop. Expansion creates more space creates more vacuum energy causes faster expansion. The acceleration compounds over time. This is the simplest explanation for dark energy. But there's a massive problem called the cosmological constant problem. When physicists calculate what the vacuum energy density should be based on quantum field theory, they get an answer that's roughly 10 to the 120th power times larger than what we observe. That's 1 followed by 120 zeros. The theoretical prediction and the observed value differ by 120 orders of magnitude. This is the worst prediction in the history of physics, arguably the biggest unsolved problem in theoretical physics. Something is either catastrophically wrong with our understanding of quantum field theory, or there's some mechanism canceling out most of the vacuum energy, leaving only a tiny residual amount. Nobody knows what that mechanism might be or why the cancellation would be so precise but incomplete. Alternative explanations suggest dark energy might not be constant. It could be a dynamic field, something that changes over time. This is called quintessence, named after the ancient concept of the fifth element beyond earth, water, air, and fire. In quintessence models, dark energy would be a field filling space with energy density that can vary. The field might have been weaker in the past and might become stronger or weaker in the future. This would change how dark energy affects the universe's expansion over time. Some models suggest dark energy could even reverse, turning from repulsive to attractive. This could eventually halt the expansion and cause the universe to recollapse in a big crunch. But current observations suggest dark energy has been roughly constant for billions of years. There's no evidence of it changing, and if it is constant, the universe will expand forever with ever-increasing acceleration. Regardless of what dark energy is, its existence has profound implications. Dark energy makes up approximately 68% of the universe's total mass energy content. Dark matter is about 27%. Normal matter is about 5%. Think about that. We live in a universe where 95% of everything is stuff we don't understand. 27% is dark matter that we can't see but know exists because of its gravitational effects. 68% is dark energy that we can't see but know exists because it's accelerating the expansion of space. Only 5% is normal matter, the stuff that makes up stars and planets and gas and dust and us. And even that 5% is spread so thin across such enormous distances that it might as well be absent in most locations. The universe is dominated by things we fundamentally don't understand. This should be humbling. We pride ourselves on scientific understanding, on explaining how the universe works. We've decoded the atom, mapped the human genome, sent probes beyond the solar system, detected gravitational waves. We understand chemistry, electromagnetism, nuclear forces, quantum mechanics, relativity. But when we look at the universe as a whole, we have to admit that most of it is a mystery. We can measure dark matter's effects but can't identify what it is. We can measure dark energy's effects, but have no accepted theory for what causes it. We're like ancient astronomers who could track the planet's motions, but didn't know planets were worlds, or that Earth was a planet itself. We can measure and predict, but we don't deeply understand. And this lack of understanding makes the emptiness more disturbing. It's not just that space is mostly empty. It's that the small amount of stuff that does exist is mostly unknown. So the universe isn't just empty in the sense of having a lot of space between objects. It's empty in the sense that most of what exists is invisible, and we don't know what it is, and the parts we can see are vanishingly rare. But there's another layer to this emptiness. Cosmic voids. When astronomers map the distribution of galaxies across large volumes of space, they discover that galaxies aren't randomly distributed. They cluster together in groups, and those groups form larger structures called superclusters. And those superclusters are connected by filaments of galaxies stretching across hundreds of millions of light years. And between these filaments are voids, enormous regions where almost no galaxies exist. Let me describe what this looks like in more detail, because the structure is remarkable. In the 1970s and 80s, astronomers began creating three-dimensional maps of galaxy positions. They measured not just where galaxies appear on the sky, but how far away they are. Distance is measured using redshift. Light from distant galaxies is stretched by the expansion of space, shifting toward longer, redder wavelengths. The more redshifted a galaxy, the farther away it is. By measuring redshifts for thousands, then millions of galaxies, astronomers could plot their three-dimensional positions in space. And a pattern emerged. Galaxies aren't scattered uniformly like stars in the night sky. They're arranged in an intricate web-like structure. Long filaments of galaxies, sheets of galaxies, clusters where filaments intersect. And between these structures, voids. The first large void was discovered in 1980, one by Robert Kirshner and colleagues. They were surveying galaxy positions in the constellation Boötes. They expected to find galaxies distributed more or less evenly. Instead, they found a region with almost no galaxies at all. A sphere roughly 330 million light-years in diameter containing only about 60 galaxies. This became known as the Boötes void. To understand how empty this is, consider that a typical region of that size contains about 10,000 galaxies. The Boötes void has 60. That's 99.4% fewer galaxies than expected. It's not completely empty. There are those 60 galaxies, mostly small dwarf galaxies and a few larger ones. But it's as close to empty as you can get while still being part of the observable universe's structure. An observer on a planet in a galaxy in the center of the Boötes void would look out in every direction and see almost nothing. The nearest significant concentration of galaxies would be more than 165 million light-years away in any direction. For comparison, our nearest large galaxy neighbor Andromeda is only 2.5 million light-years away. We're in a relatively crowded part of the universe. The Boötes void observer would see virtually no galaxies without an extremely powerful telescope. The night sky would be profoundly dark. The cosmic microwave background radiation would still be there. The faint afterglow of the Big Bang filling space with microwave frequency light. But in visible light, there would be almost nothing. No Milky Way band across the sky because the observer's own galaxy would likely be a small dwarf galaxy without a prominent disk. No neighboring galaxies visible to the naked eye. Just darkness. After the Boötes void was discovered, astronomers looked for others and found them everywhere. Voids are not rare. They are the dominant feature of the universe's large-scale structure. Most of the universe's volume is void. The giant void, also called the Capricornus void, is about 1 billion light-years across. It contains very few galaxies, most of them small and faint. The Eridanus supervoid is similarly large, about 1 billion light-years in diameter. This particular void is interesting because it corresponds to a cold spot in the cosmic microwave background. The cosmic microwave background is the radiation left over from the Big Bang. It fills the entire sky with light at a temperature of about 2.7 Kelvin, just above absolute zero. This temperature is remarkably uniform in all directions. Variations are tiny, only about 1 part in 100,000. But those tiny variations are significant. They represent density fluctuations in the early universe that later grew into galaxies and clusters and voids. The Eridanus supervoid shows up as a region that's slightly colder than average in the cosmic microwave background. This cold spot is puzzling because it's larger and colder than theoretical models predict it should be. If there's a giant void in that direction, photons traveling through it would lose energy climbing out of the void's gravitational influence, making them appear colder. But the observed cold spot is more extreme than expected for even a void as large as the Eridanus supervoid. Some physicists have speculated this might be evidence of something exotic. perhaps a collision between our universe and another universe in a multiverse. More likely, it's just an unusually large void combined with statistical fluctuation, but it shows how mysterious and extreme cosmic voids can be. The local void is much closer to us, only about 150 million light-years away. It's only about 450 million light-years across, smaller than the giant void or Boötis void, but it's still impressively empty. The local void is bounded by the local sheet, a structure that includes our local group of galaxies, the Milky Way, Andromeda, and about 80 other smaller galaxies. We're on the edge of this void, looking into it. The dipole repeller is a structure associated with the local void. It's a region of underdense space that appears to be pushing our local group away from it. This is a gravitational effect. The void doesn't push directly because it's empty, but the overdense regions surrounding the void pull matter toward them. From the perspective of matter inside or near the void, this creates an apparent repulsion from the void's center. Matter flows away from voids toward filaments and clusters. This has been confirmed by observations of galaxy velocities. Galaxies near voids tend to be moving away from the void center. Galaxies in filaments tend to be moving along the filament toward clusters. The whole structure is dynamic, with matter flowing from underdense regions to overdense regions over hundreds of millions of years. But voids don't fill in over time. They're not temporary features that will eventually disappear as matter flows into them. In fact, voids are growing. As the universe expands, matter in underdense regions becomes even more spread out, while matter in overdense regions becomes more concentrated. The rich get richer and the poor get poorer, cosmologically speaking. Voids expand faster than the average expansion rate, because they have less matter to slow the expansion locally. Filaments and clusters expand more slowly or even contract, because their higher density creates stronger gravity. So the cosmic web structure is becoming more pronounced over time. Filaments are becoming denser and voids are becoming emptier. Eventually, many billions of years from now, most of the matter in the universe will be concentrated in isolated clusters of galaxies, separated by enormous voids containing almost nothing. Dark energy accelerates this process. As expansion accelerates, voids grow even faster. Matter has less time to flow from voids to filaments before expansion carries it beyond reach. So dark energy is actively destroying the universe's structure, stretching it apart, making voids larger and more dominant. The universe is evolving toward maximum emptiness. Within voids, the environment is profoundly different from regions like ours. We live in the local sheet, a relatively dense structure. There are dozens of galaxies within a few million light-years. The night sky is rich with stars and galaxies if you have a telescope. Star formation is ongoing in the Milky Way and other nearby galaxies. New stars are born, old stars die. The cycle continues. In a void, conditions are harsher for galaxy formation and star formation. The few galaxies that exist in voids tend to be small, dim, and low in star formation. They're called void galaxies. Void galaxies are typically dwarf galaxies, much smaller than the Milky Way. They contain less gas, the raw material for star formation. They're more isolated, rarely interacting with neighbors, because there are so few neighbors. Galaxy interactions trigger star formation by compressing gas, so void galaxies miss out on this. They evolve more slowly, forming stars at lower rates, aging more gradually. Some void galaxies are among the most pristine, unchanged objects in the universe. They've been isolated for billions of years with no major interactions or mergers. They still look similar to how they looked billions of years ago. This makes them valuable for studying galaxy evolution, because they're like fossils, relatively unchanged since the early universe. But it also means void galaxies are lonely, isolated, quiet. A civilization arising in a void galaxy would have a very different view of the universe than we do. They would see far fewer galaxies in their sky. They might conclude they live in a much emptier universe than they actually do. Their cosmology would be different, based on observations that don't include the rich structure we see from our vantage point. They might discover the cosmic microwave background and realize the universe had a hot, dense beginning. But they might not realize that most of the universe is arranged in filaments and clusters. They might think their lonely void is representative of the entire cosmos. It's a sobering thought. Our understanding of the universe is shaped by where we happen to be located. We're lucky to be in a relatively dense region where galaxies are common and the cosmic web is visible. If we were in a void, our cosmology would be poorer, our observations less rich. Location matters even on cosmic scales. The existence of voids also tells us something important about the early universe. The pattern of filaments and voids we see today originated from tiny density fluctuations shortly after the Big Bang. Regions that were 1 part in 100,000 denser than average collapsed over billions of years into filaments and clusters. Regions that were 1 part in 100,000 less dense than average became voids. So the structure we see today is the amplified echo of quantum fluctuations from the first moments of cosmic history. Those quantum fluctuations determined where galaxies would form, where voids would empty out, where we would end up. If the fluctuations had been slightly different, the pattern would be different. Galaxies would be in different locations. The Milky Way might be in a void instead of a filament. Earth might not exist, because the gas cloud that formed the solar system might have been in a region that didn't collapse into a galaxy. We owe our existence to the specific pattern of density fluctuations in the early universe. And that pattern includes voids. Voids aren't failures of structure formation. They're an essential part of the cosmic web. You can't have overdense regions without underdense regions. The matter that went into filaments and clusters had to come from somewhere. It came from the voids. So voids are where the universe sacrificed density to create the structures we see. And as the universe continues expanding, voids will grow larger and more dominant, until eventually, trillions of years from now, most of the observable universe will be void. The few remaining galaxy clusters will be isolated islands in an ocean of emptiness. Let me explain how expansion works in more detail, because this is crucial to understanding why emptiness is increasing. Space itself is expanding. It's not that galaxies are moving through space away from each other. It's that the space between galaxies is growing. This is a subtle but important distinction. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're traveling across the surface, but because the surface itself is stretching. Every point on the surface is moving away from every other point. There's no center to the expansion on the surface. From any dot's perspective, all other dots are moving away. The universe works the same way, but in 3 dimensions instead of 2. Space is stretching uniformly in all directions. And the farther apart 2 objects are, the faster they appear to recede from each other, because there's more space between them to stretch. This is described by Hubble's law, discovered by Edwin Hubble in 1929. Hubble measured the distances to galaxies using Cepheid variable stars, pulsating stars whose brightness varies predictably. By measuring the period of pulsation, you can determine the star's intrinsic brightness. Compare that to how bright it appears, and you can calculate its distance. Hubble also measured the redshifts of these galaxies, which tell you how fast they're receding. When he plotted distance versus recession velocity, he found a linear relationship. Galaxies twice as far away were receding twice as fast. Galaxies 3 times farther away were receding 3 times as fast. This was revolutionary. Before Hubble, most astronomers thought the universe was static, eternal, unchanging. Some galaxies were moving toward us, some away. But the universe as a whole wasn't going anywhere. Hubble's observations showed that wasn't true. Every galaxy in every direction was moving away from us. And the more distant the galaxy, the faster it was receding. The only explanation was that the universe itself is expanding. Space is growing, carrying galaxies apart. The rate of expansion is described by the Hubble constant. This is the ratio of recession velocity to distance. Current best measurements put the Hubble constant at approximately 70 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years. So for every 3.3 million light-years of distance, recession velocity increases by 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second, and so on. At some distance, the recession velocity reaches the speed of light. This happens at approximately 14 billion light-years in the current universe. Beyond that distance, galaxies are receding faster than light. This doesn't violate relativity, because they're not moving through space faster than light. Space itself is expanding faster than light can traverse it. Light leaving a galaxy receding faster than light will never reach us. It's emitted in our direction. But space is expanding between us faster than the light can cross it. The light makes progress, but the distance it needs to cross increases faster than it can travel. It's like swimming upstream in a current faster than you can swim. You're making forward progress through the water, but the water is carrying you backward faster, so you move backward overall. Light from these distant galaxies is carried away from us by expansion despite traveling toward us through space. This defines the edge of the observable universe, the cosmological horizon. Objects beyond this horizon are causally disconnected from us. We can never observe them, never interact with them, never receive information from them. They exist presumably, but they're forever beyond our reach, and here's the critical point. This horizon is moving inward over time. As the universe continues expanding, and that expansion accelerates due to dark energy, more and more galaxies cross the horizon and disappear from view. Right now we can see galaxies about 6.5 billion light-years away in any direction. That's the current radius of the observable universe. But many of those galaxies are already receding faster than light. We see them only because the light we're receiving left those galaxies billions of years ago, when they were closer, and when expansion was slower. The light that's leaving those galaxies now will never reach us. And galaxies that are currently within our observable universe, but near the edge, will eventually cross the horizon as expansion continues. Let's trace what happens to a specific galaxy over time. Consider a galaxy currently 10 billion light-years away. That galaxy is receding from us at approximately 700,000 kilometers per second. That's more than twice the speed of light. We can see this galaxy because we're receiving light that left it 10 billion years ago when it was much closer. But that galaxy is now crossing or has already crossed our cosmological horizon. In the far future, light from that galaxy will be so red-shifted that it becomes undetectable. The wavelengths will stretch to meters, miles, eventually light years. The photons will have so little energy they might as well not exist, and new light leaving that galaxy will never reach us at all. From our perspective, that galaxy fades away and disappears. Now consider galaxies that are currently closer, say 5 billion light-years away. These galaxies are receding slower, maybe 350,000 kilometers per second. Still faster than light, but less extreme. We can observe these galaxies fairly easily with modern telescopes. But over time, as expansion continues and accelerates, these galaxies will also recede faster and faster. Eventually, they too will cross the horizon. The observable universe is shrinking from the outside in. The most distant galaxies disappear first, then slightly closer ones, then closer still. Given enough time, only our local group remains visible. But there's a limit to this shrinkage, because gravity holds structures together. Objects that are gravitationally bound don't participate in cosmic expansion. The Milky Way and Andromeda are gravitationally bound, moving toward each other on a collision course. The expansion of space has no effect on this, because gravity is stronger than expansion on this scale. Our local group contains about 80 galaxies, all gravitationally bound. They will eventually merge into a single large elliptical galaxy over the next several billion years. This merged galaxy will remain intact despite cosmic expansion because it's held together by its own gravity. Similarly, our local supercluster, the Laniakea supercluster, contains about 100,000 galaxies. Gravity binds this structure loosely. Some parts of it may remain gravitationally connected over time, but beyond the supercluster scale, expansion dominates. Galaxy clusters not bound to our supercluster are being carried away. The Virgo cluster, the Fornax cluster, the Coma cluster, all these structures are receding from us. Over tens of billions of years, they'll cross the horizon and disappear. Eventually, observers in what remains of our local group will look out and see only their own merged galaxy. Maybe a few satellite dwarf galaxies if they remain bound. But everything else will be gone, carried beyond the horizon by accelerating expansion. The cosmic microwave background will also fade. Right now, the CMB is detectable as microwave frequency radiation at 2.7 Kelvin. But as space expands, this radiation gets redshifted to longer wavelengths and lower energies. Over trillions of years, it will be redshifted into radio waves, then even longer wavelengths. The temperature will drop below 1 Kelvin, below 0.1 Kelvin, approaching absolute zero. Eventually, it will be so diffuse and low energy that it's undetectable with any conceivable technology. The CMB, the most direct evidence we have of the Big Bang, will be erased by expansion. Future civilizations won't be able to observe it. They won't know the universe had a hot, dense beginning. They might develop physics and chemistry, and understand stars and planets, but cosmology as we know it would be impossible. They'd have no way to discover the Big Bang, no way to measure cosmic expansion, no way to infer the universe's history. They'd be observationally isolated, trapped in a single galaxy or small group of galaxies with no evidence that anything else ever existed. This has led some physicists to wonder what we might be missing. Are there aspects of cosmology that we can't access because they've already been erased by expansion? Were there structures or events in the very early universe that we have no evidence for because all traces have been redshifted beyond detection? Possibly. We can observe back to the cosmic microwave background, which formed about 380,000 years after the Big Bang. Before that, the universe was opaque to light, too hot and dense for photons to travel freely. So we have no direct optical observations of the first 380,000 years. We can infer what happened using physics and theory, but direct observation is impossible. Could there have been interesting structure or events during that time that left no observable traces? We might never know. Similarly, there might be structures or phenomena beyond our current cosmological horizon that we have no way to detect. The observable universe might be a tiny fraction of the total universe. Everything beyond our horizon is unknowable to us. This is humbling. We can map and measure and understand the observable universe, but we have to accept that this might be only a small sample of all that exists, and that sample is shrinking over time as more objects cross the horizon. The universe we can observe is getting smaller while the total universe continues getting larger. Our window on reality is closing. In this context, we're fortunate to exist now, in an era when the universe is still observable, when distant galaxies are still visible, when the CMB is still detectable, when we can still measure expansion and infer the Big Bang. A few trillion years from now, this won't be possible. Future civilizations will have less information than we do. They'll inherit a lonelier, darker universe. And this raises profound questions about our place in cosmic history. Are we early or late in the universe's timeline? The universe is approximately 13.8 billion years old. Stars will continue forming for at least 100 trillion years, possibly much longer. So we're only about 0.01% of the way through the star-forming era. We're incredibly early. Most of the stars that will ever exist haven't formed yet. Most planets haven't formed. Most opportunities for life haven't happened yet. We might be among the first civilizations to arise in the universe, or we might not. Perhaps intelligent life is common and we're typical. Perhaps it's rare and we're unusual. We don't know. But what we do know is that we exist at a time when the universe is maximally observable. In the deep past, the universe was too hot and dense for structure. In the deep future, it will be too empty and dark for cosmology. Right now, we're in the sweet spot. And that's not a coincidence. Life requires certain conditioned stars, planets, stable environments, billions of years of evolution. These conditions exist during the star-forming era when the universe has cooled enough for structure, but hasn't expanded so much that structure is isolated. So intelligent life, wherever it arises, will tend to find itself in this same sweet spot. This is a form of selection bias called the anthropic principle. We observe the universe to be in a life-friendly state because we couldn't exist to observe it otherwise. If the universe were too young, too hot, too dense, we wouldn't be here. If it were too old, too cold, too empty, complex structures like life probably couldn't form. So our existence at this particular time is not random. It's a consequence of the conditions required for life. But even within the star-forming era, there's a narrower window for cosmology. Right now we can see distant galaxies and the CMB. In a trillion years, distant galaxies will be gone and the CMB will be faint. In 10 trillion years, cosmology will be nearly impossible. So there's a brief period, cosmologically speaking, when the universe is both observable and inhabited by intelligence. We're in that period now, and what we're observing is a universe becoming emptier. But let's return to the present and talk about why the universe is empty in the first place. Why isn't space filled with matter? Why are galaxies so far apart? Why is dark matter spread so thin? The answer lies in the early universe and the processes that created all structure we see today. In the first moments after the Big Bang, the universe was incredibly dense and hot. All the matter and energy that would eventually form galaxies and stars and planets and us was compressed into an unimaginably small volume. We're talking about the entire observable universe, 93 billion light-years across today, compressed to a size smaller than an atom. Temperature was beyond anything we can create or even imagine. At 1 second after the Big Bang, temperature was approximately 10 billion Kelvin. At 1 millisecond after the Big Bang, 1 trillion Kelvin. At 1 microsecond after the Big Bang, 10 trillion Kelvin. Go back farther, and the temperature was even higher, reaching energies where our current physics breaks down. At these temperatures, matter as we know it couldn't exist. No atoms, no molecules, not even protons or neutrons. Just a soup of fundamental particles and energy, quarks and gluons and electrons and photons, all interacting violently in an incredibly dense, incredibly hot plasma. This state lasted only a tiny fraction of a second. As the universe expanded, it cooled rapidly. At about 1 microsecond old, quarks combined to form protons and neutrons. At about 3 minutes old, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium. At about 380,000 years old, the universe cooled enough for electrons to combine with nuclei, forming the first atoms. This moment is called recombination. Before recombination, the universe was opaque to light. Photons couldn't travel freely because they constantly scattered off free electrons. After recombination, when electrons were bound into atoms, photons could travel freely. The universe became transparent. The photons that were freed at recombination are what we see today as the cosmic microwave background. They've been traveling through space for 13.8 billion years, red-shifted by expansion from visible light to microwaves. The CMB gives us a snapshot of the universe at age 380,000 years. And what that snapshot shows is that the universe was remarkably uniform at that time. The temperature varies by only about 1 part in 100,000 across the sky. Some regions were slightly hotter, slightly denser than average. Other regions were slightly cooler, slightly less dense. But these variations were tiny, much smaller than the variations we see today. This uniformity created the conditions for structure formation through gravity. Over hundreds of millions of years, regions that started only 1 part in 100,000 denser, collapsed into the first galaxies. Dark matter formed the scaffolding, collapsing first without resistance from radiation pressure. Normal matter fell into the gravitational wells created by dark matter, concentrated enough to form stars. The first stars probably formed about 100 million years after the Big Bang. These were massive stars, hundreds of times the mass of the Sun, burning bright and dying young in supernova explosions. Later generations of stars formed from gas enriched with heavy elements from those first supernovas. Galaxies grew by accretion and mergers. The cosmic web structure emerged as matter flowed from underdense regions toward overdense regions. By about 1 billion years after the Big Bang, the large-scale structure was beginning to resemble what we see today: galaxies, clusters, filaments, voids. But here's the key point. The initial density variations were incredibly small, 1 part in 100,000. If they had been exactly zero, perfectly uniform, structure could never form. Gravity would have nothing to work with. Matter would remain uniformly spread as the universe expanded. No galaxies, no stars, no planets, no life. But equally, if the density variations had been much larger, gravity would have been too strong. Dense regions would have collapsed too quickly and violently, forming black holes directly instead of galaxies. So the amplitude of the density fluctuations had to be just right. Large enough for structure to form, small enough that structure forms gradually, allowing stars and galaxies instead of just black holes. This fine-tuning is part of why the universe is as empty as it is, and it's why we're here to observe it. We exist in the exception, not the rule, in the rare pockets of density scattered through vast emptiness. And we're conscious of that fact. We understand that we're rare, that our existence is improbable, that the emptiness surrounding us is the norm. The universe is empty because it had to be. Too dense and black holes dominate. Too empty and galaxies don't form. Just right, and we get galaxies and stars and planets and life. We are the universe's way of knowing itself. The rare places where matter organizes into structures capable of observation and comprehension. Where physics gives rise to chemistry, chemistry to biology, biology to consciousness, consciousness to science. Where the universe looks back at itself and understands why it's empty.